For every given filtration application, there exists a particle size that is the most difficult to filter or capture. This particle size, commonly referred to as the most penetrating particle size, is least affected by filtration capture mechanisms. You might wonder why this is the case and how you can use this information to better select a filter media for your specific application. We'll answer these questions in this second of a two-part video series. Hi, my name is Ken Milam. I'm an applications engineer here at ThermoPore. Welcome to Thermo TV. In this video, we'll graphically show the contribution that our 5 filtration capture mechanisms have on various size particles. Then, we'll reveal the likely size of your filter's most penetrating particle size. Lastly, we'll explain how this information can best be used to validate the integrity of your filtration system. Let's get started with a quick review of our particle capture mechanisms. In the first part of this video series, we introduced the following terms: sieving, inertial impaction, interception, diffusion, and electrostatics. Now, let's talk about the particles that each mechanism is able to influence. I've got a graph that depicts particle capture efficiency on the y-axis and particle size on the x-axis. Both the particle size and the capture efficiency increase as you travel away from the graph's origin. What I'd like to do is draw a curve for each of our filtration capture mechanisms. I'll end up with 5 curves on this graph, but let's look at each mechanism one at a time. Let's start with sieving. Sieving was defined as the mechanism that captures or filters particles that are larger than the openings in the filter. It's safe to say that this mechanism has a greater influence on large particles and virtually no effect on small particles. So we would draw a curve that looks like this to demonstrate the effect of sieving. Again, this curve graphically represents that sieving's filtration efficiency contribution increases as a particle size increases. It also suggests that its filtration contribution is minimal for particles small in size. So let's repeat the same process for the remainder of our filtration mechanisms. With inertial impaction, we discussed the notion that particles with mass have inertial tendencies that tend to make them unable to make their way through a filter. So, as you might expect, the filtration contribution made by inertial impaction is similar to sieving, i.e., larger particles with more inertia tend to get captured via inertial impaction. So, this mechanism will have a greater influence on larger particles and less of an influence on smaller particles. Interception was the next mechanism that we discussed. As you probably recall, interception influences particles that escape capture by our first 2 mechanisms, yet the particle's diameter needed to be large enough to make contact with the filter media. Therefore, interception has more of an influence on large particles and less of an influence on smaller particles. So let's draw our interception curve so that it's similar to our first 2, but slightly offset. Next, we introduced diffusion. Diffusion described capture via a particle's Brownian motion. For a particle's trajectory to be influenced by other gas molecules, you can probably infer that we're talking about a mechanism that affects very small particles. Further, you can probably speculate that as a particle gets larger and heavier, that its Brownian motion decreases. So diffusion then will heavily influence small particles, and it will make little to no influence on large particles. The same can be said for electrostatics, our 5th and final capture mechanism. Electrostatics tend to influence smaller sized particles more so than large sized particles. So again, we can draw the 5th capture mechanism curve so that it demonstrates a higher influence on smaller sized particles. Now, the important concept to realize at this point in time is that these 5 filtration capture mechanisms are always present. They're always attempting to influence a particle's capture. In other words, these filtration capture mechanisms are additive. So the resulting curve that can be drawn to summarize their influence will look something like this. Notice that there are filtration capture mechanisms that affect the smallest particles and the large particles. It's just that their combined contribution is smallest in the 0.1 to 0.5 micron range. So now, what does this mean for you? Well, your test and evaluation of your filter's performance should take into consideration particle sizes that stand the best chance of compromising your filtration system. If your filter is going to need filtration capability of filtering particles less than 10 microns, then you need to pay careful attention to the filter's capability to function and perform when it's being challenged by particles that range from 0.1 to 0.5 microns. By ensuring that your filtration media is suitable for use with particles that fall into that range, then you're effectively ensuring even better performance against particles that fall outside that range. Well, I hope this installment of Thermo TV has helped provide you with some insight into filtration capture mechanisms. And I hope that we've been able to explain the science behind the existence of a most penetrating particle size. That's it for now, but stay on the lookout for later installments of Thermo TV. As always, if you have any additional questions or if there are some topics that you'd like to see us add to the Thermo TV channel, give us a call or drop us a line. But for now, I'm Ken Milam saying thanks for watching this installment of Thermo TV. We'll see you next time.